So yeah, okay. So I would like my friend Adishri to start with the event. Adishri.
Okay, am I audible?
Yeah.
Yes.
So, welcome back everyone to the second day of the 14th annual Frontiers in Physics. Yesterday was truly an amazing experience, and the lectures were wonderful and engaging and informative, wouldn't you all say? For today, we have some more lectures in store for you, and I would like to welcome our lecturers for today. It is truly an honor for us to be able to extend our hospitality towards you. I would like to remind everyone that if they have any questions, they can ask them at the end of the lecture by raising their hand, and the host will ask them to unmute themselves, or by putting it in the chat box. Now, without further ado, let us begin with our seminar. Our first lecturer for today is Professor Bhas Bapat. I would like to ask Chitrakshi Ede to introduce him.
Hello, good morning. Today we have Dr. Bhas Bapat with us. He did his bachelor's in physics from Pune University. He did his master's from the Indian Institute of Technology and received a silver medal for the first rank there. After his PhD from TIFR Mumbai, he was a postdoctoral fellow in Albert Ludwigs University, Freiburg, Germany. His research interest is in atomic and molecular physics. He has been a faculty member at Physics Research Laboratory, Ahmedabad, an associate member at IISER Mohali, and Dean of Academic Affairs in IISER Tirupati. Currently, he is an associate professor in IISER Pune. He has also contributed in improving the undergraduate educations there. He has been awarded the Best Thesis Award of the Indian Physics Association at the 12th National Conference on Atomic and Molecular Physics, Udaipur, in January 1999, by Professor S.N. Ghosh Young Scientist Award of the Indian Society for Atomic and Molecular Physics at the 14th National Conference on Atomic and Molecular Physics, Shanti Niketan, in January 2003, and S.N. Sashedri Memorial Instrumentation Award of the year 2006 by the Indian Physics Association. He has also worked in collaboration with groups such as the Indus 1 Synchrotron in RRCAT Indore and many others, and has made many publications in his field. Today, he'll be talking about solar wind ion spectrometer aboard Aditya L-1 solar mission. We welcome you, sir.
Thank you, Chitrakshi.
Yeah.
So, am I ready to go?
Yeah, sure.
Yeah. Okay.
By the way,
So just
yeah. Okay.
Yeah, please go ahead.
Yeah, I just wanted to confirm you have been here in Ferguson College for a while.
Yes, of course. I mean, I graduated from Ferguson College in 1990.
I see.
Perhaps no one from that time is around now, but yes, I was there from 85 to 90.
I see. Okay, sir. Yeah. So, you can start now.
Okay. Yeah. So this is a very nice opportunity to talk to my fellow students from the same college, perhaps sharing the same lecture hall in better times. I mean, non-COVID times. I would really have liked to come to the college to give this talk, but given the current situation, that doesn't seem likely to happen in the near future. And in fact, Dr. Dabadi had requested me last year to give a talk in the same, the last year's edition of this physics fest that the college has every year. But for some reason, some other engagement, I could not give a talk last year. And this year I decided that whatever come what may, I must participate in this fest. And I'm really glad that this fest happens every year regularly. And I would be happy to come back to it in the later years. So what I'm going to talk about today is really something that is not very commonly known, or what is not commonly practiced in physics departments in the country, which is about building instruments for space missions. Very few laboratories in the country work on anything like this. And I'm fortunate to have been part of Physical Research Laboratory earlier, which gave me the impetus to get engaged in space instrumentation development activities. This project that I'm going to talk about took off when I was still at PRL, Physical Research Laboratory, Ahmedabad, some 6-7 years ago. And we have been, my team in PRL and I here, we have been working towards this project for the last 6-7 years. So let me begin by a very elementary overview of what kind of things we can see from the Earth and what is there in store for us when we try to look at the sun. And then after giving you an overview, I will go get to the nitty-gritty of building a space payload and describe in detail the kind of payload we are building and what we hope to achieve with it. Okay. I hope my slides are visible to you and you can see an outline at the moment. So if that's not the case, Chitrashi, please let me know if you are able to see this so that I can continue as I'm doing now. Yeah, great. Okay, so let us start looking at this at our own atmosphere first. Okay, so our own atmosphere is a fairly thin shell that protects us. We are surrounded by air, the pressure of which is constantly falling as we rise away from the ground. And a reasonable density of air molecules persists till fairly large heights, like 100-200 kilometers. But the composition of the Earth's atmosphere changes as you go up. As at lower altitudes, as you know, there is 78% oxygen, 78% nitrogen, 21% oxygen, 1% argon, and so on. This composition changes slightly as you go up. But more importantly, what changes are the kinetics. The way the molecules mix, that changes. What also changes is the fact that the relative composition of different species also changes. The temperature gradients change gradually. If you go very far away, you can imagine that since the number densities are very low, the collisions between particles become rarer and rarer, and it is not a very well mixed system at great altitudes. But what also changes, and a very significant change, happens at an altitude of about 90 kilometers, okay, so 80 to 90 kilometers, which is the transition between the mesosphere and the thermosphere. In this region, we have a layer of not neutrals, but ions. So apart from the neutral atoms and molecules that surround us, there is also a shell of ions at an altitude roughly of 90 kilometers, plus minus about, well, not plus minus equal, but maybe starting from about 70 kilometers all the way to 150 kilometers. There is a very sparse layer of ions. And the reason why this particular height is abundant with ions has to do with the fact that the light coming to the Earth from the sun contains ultraviolet and X-ray radiations, which result in ionization of the neutrals. Now you might say, why doesn't then this ion, why don't these ions occur at lower altitudes? So the reason is that the other molecules, all molecules actually absorb light in some form. So there's a delicate balance of at what altitude the number density of the neutrals is sufficient in order to have a balance of ionization and recombination. And coupled to the fact that there has to be a certain set of wavelengths available for ionization to occur. So all these three factors, the incoming flux of photons, the number density, and the composition, these three factors have an interplay which determine at what altitude a layer of ions can be formed in the Earth's atmosphere. And in the Earth's atmosphere, this happens at around 90 kilometers. In some other planetary atmospheres, this may happen at different altitudes. Now, apart from this atmosphere of neutrals and ions, we also have an invisible but all-pervading shield, if you like, of the magnetosphere. Now, the magnetosphere is nothing but the Earth's magnetic field generated by whatever is there inside the Earth. But this pervades across space. It is very weak, but it is very important. And in this cartoon, you can see the gross features of the magnetosphere. These red lines are the magnetic field lines. So like for any bar magnet, these start from one end and close at the other end of the bar. But you can see that they're getting distorted at distances far away from the Earth. So if you go to something like 10 Earth radii, as you can see in this cartoon, if you go away from the sun, which is the pointed part that you see, that is called what is called the tail of that magnetosphere, or the magnetotail, which is a combination of the effects of what the sun is doing to the magnetosphere and what the magnetosphere would have been had the sun not been there. So it's a superposition of these two effects. So there's a magnetic effect of the sun which affects the magnetosphere of the Earth. And as a result of which, the superposition of the two effects results in a magnetosphere whose field lines or whose contours can be shown as seen in the red, by the red lines in this diagram. In addition to this, there is this thing called the bow shock, which is this greenish boundary that has been shown. And this greenish boundary is, if you are aware of what happens in supersonic flows in fluids, then this is like a boundary between laminar flow and mixed flow. So something similar to that. And this bow shock is not a flow of particles, but it is the boundary between two types of shapes of the magnetic field lines. And this boundary is again driven by the sun, primarily by the sun. Now, this magnetosphere has an important role in protecting the Earth. Whenever a charged particle enters the Earth's surroundings, I'm not saying necessarily the atmosphere, but surroundings, the magnetic field lines will guide the particles. And because the magnetic field lines are aligned roughly to the geographical poles, charged particles which follow magnetic field lines will preferably be propelled or preferably be diverted towards the Earth's north and south poles. The beauty of this effect, or the beauty of this shield, is that because of this magnetic shield that we have, all the dangerous particles that would otherwise have harmed life in some form, are diverted towards the poles, and we are safe at lower latitudes, okay, closer to the equator. Of course, these fluxes are not great. They're low fluxes, but every once in a while there's a spurt of flux. You start getting a lot of changes in the outer atmosphere. These are called space weather effects. And these space weather effects can sometimes disrupt a lot of telecommunication and electrical activity, especially in Northern Europe and Northern America, when, in regions that are close to the North Pole and are populated. In the Southern Hemisphere, there's not much population, so it doesn't matter. But in the northern latitudes, excess activity of the sun, excess emission from the sun, which affects the magnetosphere here, can cause changes in weather and changes in the ionosphere that I described earlier, influencing or sometimes even disturbing or destroying electronic communication as well as electrical installations. So this is something that is very important for us. Now, why am I describing these things if I want to talk about the sun? So keep this in your reserve memory for a while. Let us now hop over to the sun. Okay, sorry, before I do that, sorry. There's one more thing I need to say. So I talked about the magnetosphere, but I want to come back to the atmosphere and highlight one more fact. See, the light that comes to us is all in the visible, or mostly in the visible part of the electromagnetic spectrum, which is this pure kind of band that is shown here. Wavelengths shorter than that, like the ultraviolet, X-rays, gamma rays, and so on, are completely absorbed by the Earth's atmosphere. So the Earth's atmosphere offers an opaque barrier to X-rays and gamma rays, or even ultraviolet rays. Somewhere towards the shorter wavelength bands, where it is like 1 or 10 micron kind of wavelengths, most of the infrared part of the spectrum also gets absorbed by the Earth's, gets absorbed by the Earth's atmosphere. If you go to even longer wavelengths, radio waves get transmitted through the Earth's atmosphere, and that is why we have things like the GMRT functioning from the ground. That is also the reason why we are able to communicate with satellites, which go well beyond the Earth's atmosphere. If you go further beyond that and go to even longer wavelengths, which is like of the order of a kilometer or 100 meters kind of wavelengths, 100 meter to 1 kilometer kind of wavelengths, these wavelengths are again not transmitted by the Earth's atmosphere. And the reason for this is the ionosphere that I described. The ionosphere acts as a metallic boundary or as a conducting boundary, and this reflects the radio waves coming in and it reflects back to the Earth radio waves that are generated from the Earth if their wavelengths happen to be of the order of 100 meter or a kilometer. And the reason why this is wavelength selective has to do with the fact that the mean free path or the density of ions in that layer has a certain value. So if some of you who are perhaps in the third year of BSc would have studied some electricity, magnetism, and some bits of radiation, and you can probably quickly relate to the fact that a layer of ions or reasonably thin, reasonably thick layer of ions will block the transmission of radio waves or any radiation. Okay? So that is really the thing that is happening in the Earth's atmosphere. And because there are these boundaries, or rather bands or windows, which allow certain wavelengths to pass and some other wavelengths not to pass or to remain opaque, the Earth's atmosphere actually has windows to the outside world. We don't see the outside world completely. We only see certain parts, and the information that we have is primarily governed by which wavelength bands are transmitted by the Earth's atmosphere. So if you wanted to see gamma rays coming out from some distant star, for instance, or if you wanted to see something in the infrared, or you wanted to see something in the very long wavelengths, sitting on the Earth would do you no good. Sitting on the Earth would completely block these wavelengths that are shown in this diagram. Now, what does the sun do? The sun is a very active object. It has a lot of thermonuclear reactions happening in its core meaning the central inside part. Then there are many other processes that lead to finally the external surface of the sun, which we see, the photosphere, which is where most of the visible light or the IR radiation that corresponds to the black body equivalent of the sun at 6500 Kelvin. All of those processes, the sun mimicking the black body, these are all surface processes. What happens inside are intense thermonuclear reactions, which result in the formation of heavier nuclei starting from protons. Okay, so hydrogen fusion causes helium, helium fusion causes lithium, and so on. So this entire nucleosynthesis, starting with protons, happens at the core of the sun. These are extremely energetic reactions, and that is the reason why so much energy is constantly being given out by the sun. Okay. But what is the kind of energy the sun gives out? Okay. So the sun gives out practically all wavelengths of energy. And if you remember, only a small part of it, which corresponds to the visible part, and a little bit of infrared, reaches us through the atmosphere. If you want to see how the sun looks in the gamma ray spectrum, or in the gamma ray wavelengths, or in the UV wavelengths, we will not be able to figure this out sitting on the Earth. We'll have to leave the Earth's atmosphere in order to see these effects. Now, what you're seeing here is a very nice red, yellow, white, black picture, which is typically what is called a hot body or a black body equivalent. But what you're seeing here is actually a false color image. Okay? The white parts are where the energy is maximum, and the dark parts are where the energy is lesser. But what I want you to remember is that a large part of our information about the sun has come from the observation of one particular wavelength, which is called the hydrogen alpha wavelength, which is nothing but the n is equal to 3 to n is equal to 1 transition in the hydrogen atom. So this wavelength has a very deep red color, which is about 6,530 something, 653 nanometer. This is a deep red color. And this deep red color is because of the recombination processes happening in the sun in the hydrogen atom. Most of the contents of the sun are really hydrogen atoms or hydrogen nuclei. And whenever there is a recombination happening, meaning an electron getting attached to the proton and hydrogen getting formed, it results in a cascade of transitions. And among these, the n is equal to 3 to n is equal to 1 transition is a very strong transition that we can observe from the Earth. It is visible, it is at 653 nanometers, and it is a very intense transition. Now, those of you who are again in the third year or perhaps in the second year might have heard of an effect called the Zeeman effect. The Zeeman effect is the influence of the magnetic field on a spectral line. If you have a spectral line which is, say, emitting light, in this case, say, corresponds to 653 nanometer, There is something called a fine structure to this, which means that the nuclear spin and the orbital angular momentum, they interact and result in a splitting of the wavelength or splitting of the line, which means that instead of being just one wavelength, there are 3 or 5 very narrowly separated but distinct transitions. So small differences in wavelengths. The splitting of these wavelengths depends on the magnetic field. Now, if you apply an external magnetic field, you can force these lines to move apart. Okay, you can force the separation of the lines to increase by putting an external magnetic field. Now, if the sun had a magnetic field of its own, then the Zeeman line in the laboratory, corresponding to a hydrogen atom n is equal to 3 to 1 transition under ideal conditions in the laboratory, would have a slightly different set of wavelengths compared to what happens in the sun, if the sun had a magnetic field. This tiny difference in the wavelengths enables us to measure the magnetic field of the sun. The beauty, again, taking this idea several steps further, is that you can actually look at very small parts of the sun at a time by specialized instruments and map out the entire magnetic field on the surface. So at different parts of the sun, on the different parts of the sun, if the wavelengths of this H alpha line are slightly different, or they are slightly, the splittings are slightly changed, then that means that the magnetic field locally has changed or is different from somewhere else. And that allows you to map the entire magnetic field by simply looking at the sun in the H alpha band of the spectrum. And that's a remarkable thing that is possible. And all of this is possible sitting right here on the Earth. Now, you will be surprised to know that the sun has been observed for as long as 400 years, sitting on the Earth again. Nobody went out of the atmosphere. And what was looked at was just the entire white light, but also this particular transition in the hydrogen atom. Of course, in 1600 or 1700 or 1800, the structure of the hydrogen atom was not well known. But still, people could make observations using some filters and some telescopes and some optical instruments. And what they found, quite remarkably, is that there are dark spots on the sun, which are called sunspots. The sun is not entirely uniformly bright. And these dark spots change in intensity and number as a function of time. And there is sort of an 11-year period to the number of sunspot or their oscillations, the oscillation of the number of sunspots. And this pattern has persisted to date. So this 11-year solar cycle is one very, very distinctive feature of the activity on the sun. So this is all this that I've told you is the information that we have. I mean, there's of course much more information, but what I've told you so far is information based on light, based on observation of light. But now, what the sun is actually doing, as I showed you in the earlier picture also, is that besides light, the sun is giving out or is throwing out large amounts of particles, massive particles. Okay. And they're mostly protons and alpha particles, but there are also heavier nuclei. Now, this massive stream of particles emerging from the sun is called the solar wind. You might have heard of this term. So solar wind is really stream of particles, mostly protons and alpha particles, emerging from the sun in all directions. Every once in a while, because of thermonuclear processes combined with the magnetic field of the sun has a large magnetic field because of large number of ions forming current sheets. Okay. So these, the interplay between the magnetic field and the charged particles causes a lot of instabilities on the sun. Every once in a while, you have what is called a solar flare or prominences, which are large ejecta, massive ejecta from the sun. Now, the solar wind comes out of the sun, emerges from its ionosphere or its own upper atmosphere, which is called the corona. And the flux of these particles is a direct indicator, or it carries the signature of the activity, which means, when I say activity, I mean different kinds of thermonuclear processes and magnetic instabilities that are constantly changing or constantly evolving on the sun. And this solar wind, as I showed you in the first picture, as it approaches the Earth, it enters the Earth's magnetosphere, and these particles get deflected towards the poles. When these particles get deflected towards the pole, they interact with the neutral atoms and molecules in the Earth's atmosphere in the polar regions, and they cause these remarkable features called aurora australis and aurora borealis, which can be seen at random times from regions close to the poles. But can we see this solar wind? No, we cannot, because the Earth's atmosphere is shielding us. Okay. The Earth's atmosphere shields us, so if we really want to see the solar wind, we'll have to get out of the atmosphere. And people started doing this some 30, 40 years ago when satellites were slowly becoming the norm for observations and for communications. And with observations over the last 50 or 60 years, what has been found is that the solar wind, these particles, they are actually free-flowing particles. So you can now imagine that it is that there's a very thin, very sparse current emerging from the sun and spreading across the solar system. Somewhere in the solar system, there's a tiny spot called the Earth, and a small flux reaches the Earth as well. There's nothing remarkable about it. You would find the same thing happening anywhere in the solar system. But because the Earth has a magnetic field, these particles never manage to reach, well, not just the magnetic field, not just the magnetosphere, but also the atmosphere. These particles never manage to reach the surface of the Earth. But when observed from satellite-borne instruments or observatories, what is found is that the solar wind or these solar these streaming particles actually are thrown out or are ejected in the form of a spiral as seen from the sun. Okay, so you can do this exercise and do a transformation from a rotating frame to a static frame, and you'll find that something that goes radially in the static frame, the center of mass frame, will appear as a spiral if the source itself is spinning. Okay, so that is what you see in this diagram, that the solar wind comes out in the form of a spiral. But the other remarkable thing is that this solar wind, the particles in the solar wind, are almost expanding or evolving or moving out radially without any collisions. So the number densities are very small. So once this particle leaves the solar corona, they essentially evolve freely. But now, since there is nothing else in the path, what happens is that each particle is generating a magnetic field, which in turn is going to affect the path of all the other atoms, other protons and alpha particles that are part of the solar wind. So in some sense, you could say that because this is a free flow of charged particles, there's an associated magnetic field, which in turn drives the motion of other particles. So it is like saying that the magnetic field is frozen into the motion of the solar wind itself. So this is a very peculiar phenomenon, and this happens because the evolution of this solar wind is essentially a collision-free process, and these are free charge particles, or current sheets, if you like, or current beams, if you like, that are passing through empty space in the solar system. Okay. What else do you know about the solar wind? Okay, so these particles, the protons and the alpha particles, they do not all have the same energy. So this is a graph showing how many particles there are at a particular energy. So I don't want you to pay too much attention to the numbers, except for a couple of things, which is that most of the particles, most of the protons or alpha particles that are emerging from the sun have an energy which is of the order of 1 kiloelectron volt. And the peak flux is about 10 to the 16 in some units, which is per centimeter square, per steradian, per MeV, per nucleon. Okay. That's a fairly longish unit, but that's a standard unit that's used to describe particle fluxes. So the peak of the energy is about 10 to the 16 particles. And most of the particles have an energy which is close to 1 keV, which corresponds to 400 kilometers per second, as was shown in the previous spiral diagram. The energy distribution is not very simple. So if you look at the kinetic energy distribution of particles in a gas, you know that this is a Maxwellian distribution. And if you have something else like particles effusing out of a container, then the distribution changes. If you have particles emerging from a very high pressure zone to the low pressure zone, you get supersonic flows. And again, the particle kinetic energy distributions are different. Similarly, here, there is no single distribution that describes the entire spectrum. There are different parts and different approximations are made in order to describe the spectrum. Now, why is the shape of the distribution not smooth? Well, there are many conjectures about this. We don't know for sure yet, and that is where the research really is underway. One part of the research in solar physics is about understanding why the energy spectrum is the way it is. So the energy spectrum is the way it is. Partly, the part of the things that we know is that some part of the spectrum, which is the main peak that you see in this, corresponds to processes that are happening directly on the sun. Then there is this long tail, which is the energization, which is believed to be a result or an outcome of processes that happen once the solar wind leaves the corona. So these are things happening outside the solar corona, which is called energization, which is increasing the energy because of interplanetary fields and so on. As you can see, the Y scale, the intensity scale is logarithmic. So the energization already, although it looks to be a dominant feature, is actually here 8 orders of magnitude lower than the peak. The flux is really very small, but it is there. And it is these small features which really hold the key to explaining or understanding processes that might be happening in the interplanetary space. Another thing which I wanted to point out, which is a little tricky to understand, but nonetheless I'll put it here. So any anisotropy that we talk about, okay, I'm sure all of you are familiar with anisotropy. It just means that some physical quantity or some parameter has different values in different directions in space. That's all that anisotropy means. Okay. So I could define anisotropy for X or for something. I could define anisotropy for, say, energy. I could define anisotropy for velocity. I could simply define anisotropy for the distribution of particles. Okay. When I talk of anisotropy of distribution of particles, all it means is that in a particular direction there are more particles than in some other direction. So in this case, what I have defined is a ratio beta, which is the ratio of the kinetic energy of the particles in the solar wind to the magnetic energy, so the field energy. So the energy in a magnetic field is half mu naught b squared, and the kinetic energy is simply half mv squared. So this ratio beta is what I'm interested in. Now, why am I interested in this? Because, as I said, that the interplanetary fields and the magnetic fields determine how the kinetic energies change or how the directions of particles change. They don't change the kinetic energy directly, but they do change the direction of the particles. Now, if I look at the kinetic energy of particles emerging in a particular direction versus the kinetic energy distribution of particles emerging in a direction perpendicular to the chosen one, this anisotropy will tell me something about the magnetic field. And that is the reason why I define these two quantities, beta perpendicular and beta parallel, which is essentially the ratio of the kinetic energy to the magnetic energy for particles streaming parallel to the magnetic field and particles streaming perpendicular to the magnetic field. And what magnetic field are we talking about? We are talking about the magnetic field at some point in the interplanetary space. So this is another feature of the solar wind that people have observed in past observations, and all of these observations have to be done from outside the atmosphere. The last feature that I want to talk about is that the main components of the solar wind are alpha particles and protons. Now, normally this ratio of alpha particles to protons is about 5 to 8%. Sometimes this ratio goes down. Sometimes this ratio goes up as high as 35%. okay, for very short periods. And all this is known from past observations. Why does this happen? Now, this happens primarily because of increased solar activity. There's a lot of thermonuclear activity happening in the sun. Then the fusion rates increase, and that causes disturbances in the sun. And it's a very complicated process. It's not as simple as I'm trying to make it out. But this may result in excess helium being formed. And the helium not only has to be formed, it also has to be ejected for us to be able to see it. And by a complicated set of processes, it so happens that there is excess helium being thrown out whenever the activity on the sun changes. So people have been interested in measuring this ratio and studying this ratio and relating it to the processes happening on the sun. For instance, a general observation based on correlation of data sets has been that if the helium to proton ratio, so alpha particles, not helium, alpha particle to proton ratio, which is He double plus by H plus, if this is in excess of 8%, then it means that there is a process called coronal mass ejections, which is a process in which vast amounts of solar mass is thrown out from the surface. So there are a whole lot of processes that happen, and each of these is signaled by changes either in the helium to proton, or rather alpha to proton ratio, or change in the beta values, or change in the energy spectrum. As I've been saying earlier, for all these measurements to be possible, where you have to actually detect particles, it is necessary that we leave the Earth's atmosphere. Because the Earth's atmosphere and the magnetosphere is going to block everything, block these protons and alpha particles. So it becomes necessary to establish an observatory that will detect these particles, which has to be a space-based observatory. So we have to leave the Earth's atmosphere and go to space, maybe in an orbiting satellite, or maybe somewhere else. Now, one very popular is not really the right word. Popular means something slightly different, but nonetheless, I'm tempted to use the word popular. One such popular and a very useful location for such observations is what is called the Lagrange point. And this is where I would now switch gears and come to what kind of instrumentation we need for doing these studies. If you have any questions, this may be a good point to pause and take a few questions. So Chitrakshi, can we do that?
Yes, we can. Or maybe we can take all the questions at last. Is that okay with you?
No, so what I would prefer if, these questions related to the structure of the sun and so on are done first and the instrument part comes later.
Yeah, okay, no problem.
Okay. We have one question from Baljit. Baljit, you can
sure, go ahead.
Unmute.
Yes. Hello, sir. I wanted to ask the magnetic field of the Earth, the strength of the magnetic field of the Earth, even at its surface, is ranging from 0.3 Gauss to 0.6 Gauss.
Yes.
So, how is it strong enough in space to deflect all the energetic particles that arrive by solar?
Right. Good question. So, see, what one has to remember is that the magnetic force is V cross B. So, if B is small but V is large, the force can still be quite large. The other thing is that you have a deflection, and if the path length is long, then the deflection, the spatial deflection, not the angular deflection, the spatial deflection can be very large over long path lengths. Right? So this magnetic field actually pervades a very large space. So if you can see in this diagram, this is not to scale, but the previous one was to scale. The magnetic field, spreads out to something like 10 or 20 Earth radii. If the particle experiences a weak force at a great distance, by the time it reaches the sun, reaches the Earth, it would have deflected very significantly. And where would it have deflected? It would have followed the field lines and gone towards the pole. If the particle energy is extremely high, like it happens for cosmic rays, then these cosmic rays, they are not perturbed by the magnetic field. They just come down straight. But their numbers are small, much smaller. The range for which the magnetosphere is a very effective shield is a range from anything in the low energy to about a mega electron volt or so. Okay? Beyond that, tens of mega electron volts. Beyond that, of course, the particles can actually come through the Earth's atmosphere straight at any point on the Earth, but they will suffer a lot of collisions on the way with the neutral molecules. Does that answer your question? Hello?
Yeah, I guess it answered.
Yeah, I don't see any other hands here, so I think.
Okay, so let us proceed.
Okay.
So one such point, one such very important and very useful point, a vantage point for making observations concerning the sun is what is called the Lagrange point. Now, what is a Lagrange point? Take any two-body system, take any two-body gravitating system, one the lighter mass going around the heavier mass. There are 5 points in the plane of the orbit where the gravitational force, the difference between the gravitational force, I shouldn't say the difference, they are in opposite directions. So the sum of the gravitational forces exactly balances the centripetal force required for a small object to perform stable motion. So, for example, the easiest point to understand is the first Lagrange point, which is shown as L1 here. This is the place where the gravitational pull of the Earth and the gravitational pull of the Sun are along the radial line, both along the radial line, on a mass that is situated here. So a small mass situated here would be pulled by the Earth in this direction and pulled by the Sun in that direction. But at some point, the two forces will balance out. And a particle that has a small velocity in the tangential direction here will continue to remain there without losing sight of either the Sun or the Earth, because that is a stable, that is a point where the forces from the two heavy objects cancel out. You can imagine a few other things here. They are a little more complicated. I won't get into that. L1 is the easiest to understand. And if you place an object here, it will co-rotate with the Earth, go around the Sun at all times. So imagine placing an observatory here. This observatory, if you face it or if you point it to the Sun, it will give you information 24/7. Instead, if you were to try and put an observatory which revolves around the Earth like all satellites do, then for half of the time you will not be able to see the Sun at all. And depending on the inclination of the orbit and so on, the amount of time that the satellite will actually directly be able to look at the Sun will be a very small fraction of its total lifetime. Instead, if you put a satellite here, that satellite will be able to look at the Sun at all time, for all times. This Lagrange point, unfortunately, is not very close. It is about 1.5 million kilometers away. So putting a satellite there is quite a challenge. But this has been done in the past. It has been done for a few years now. And this Lagrange point, this L1 point, is a favorite location for solar observatories. And much of the data that I talked about in the earlier slides has come from observations out of satellites placed at L1, it's called the first Lagrange point, and also a little bit of data from satellites orbiting the Earth in low height orbits. But that is not so much. Much of this is from satellites at L1. Okay. So NASA, for instance, has 2 observatories which were launched in the 90s, which are located at L1, and they have a few others in the recent years which are not at L1, but they are moving in the orbit that crosses L1, this blue line. They don't exactly sit at L1, they sort of follow the path. Okay. When you place a satellite at L1, you are not only looking at the Sun directly, you are looking at it all the time. Furthermore, there is no atmosphere to block anything that is coming from the Sun. So you can look at whatever wavelengths you are interested in. You can look at the protons that are coming out, you can look at the alpha particles that are coming out, and you can also look at the heavy nuclei that also come out in very small numbers. Okay, so it's a great point for placing an observatory. But placing an observatory there is a hard task. And in 2015, the Indian Space Research Organization announced that there would be an Indian mission to go to this L1 point and observe the sun. Okay. And that is where my team then started planning this small mission, consisting of an instrument which would look at the solar proton and alpha particles. So this will, we are hoping that this mission will be launched in the middle of next year for a 5-year lifetime. This spacecraft is a fairly large spacecraft, 1900 kilograms weight. It will be launched by the PSLV XL rocket, and it will take 180 days to reach the Lagrange point. So it's quite a distance. Now, on board this Aditya L-1 satellite are several instruments. There are 7 scientific instruments. I'll not go into the details of any one of them except the one that I'm involved in, which is this Aditya Solar Wind Particle Experiment. Okay? So this is the mission that this is the payload I'm going to talk about. Okay. When mounted, this satellite is going to look something like this. All these instruments sitting here. This is a very rough, not to scale diagram. These are the solar panels which will provide power to the different instruments. Then this blue and brown box at the bottom, that is really the satellite which has all the fuel, the controls, navigation, communication, all equipment. And on the top deck are sitting all scientific instruments, which will do a variety of observations. So our instrument sits somewhere over here. There's a large instrument called a coronagraph, which is essentially an instrument to look at the H-alpha line in great detail and map out the entire sun. Then there is a ultraviolet spectrometer, there are X-ray spectrometers, and so on and so forth. All right. So let me now come to the specific instrument that we are building. The aim of this instrument, or the aim of this instrument, is to measure the angular distributions and the energy distributions of the particles in the solar wind. Now, I had spoken about this earlier, the importance of measuring the energy distributions and the importance of measuring the angular distributions. Now, you might say you already have that data, you have the energy spectrum, so why do you want to do it again? Okay. So the answer to this is the following, that what I showed you earlier is not angle resolved. We don't know how this distribution changes with different directions. And because there is a lot of interaction between the solar wind particles and the distributions, and these distributions do not change identically in all directions. And the aim of our instrument is to get these angular. Yeah, hello.
Hello. Yeah, sorry,
Hello.
we lost you in the last sentence you said. Can you please repeat?
Sorry. Yeah. So as I was saying, because of the wide spectrum of, or the wide variety of activities that happen on the sun, the distribution of the kinetic energies of the particles, or the distribution of the proton alpha ratio, is not identical in all directions, not expected to be identical in all directions. So what we would like to do is measure the energy distributions for particles coming in different directions, measure the proton alpha ratios for particles coming in different directions. And the focus mainly is to get these spectra as a function of the direction in which we are looking. So we need a multi-directional observation. And that is really the goal of this entire mission, or this payload. Not the entire mission. The entire mission has multiple objectives, but our mission is this. So we have managed to put this in a fairly small instrument, about 13 kg, including electronics. And there's a companion instrument called STEPS, which uses solid-state detectors. Yeah, I've already said what the mission objectives are. So we focus on how the energy distributions change, how the proton alpha ratio changes, and what kind of anisotropies exist in the particle distribution. Now, how are we going to do this? Okay, so 3 objectives, and I've made a table which lists the 3 objectives, lists the 3 science goals, and the corresponding observations that we wish to make. So the first observation that we wish to make is simply acquire the energy spectrum in the range 100 eV to 20 kV. That is the dominant part of the spectrum, as I showed you earlier. Then we want this angular distribution, so measure in different directions. And we also want to separate the proton and alpha and heavier ions that are coming in the solar wind. Now, how do you detect these particles? Okay, this is something that perhaps most people are not aware of, so I thought it would be a good idea to spend a little time on this. So how you detect charged particles really depends on what energies you're talking about. If you're talking about energies less than, say, 100 keV, okay, or actually even lesser than that, more like 20 or 30 keV, then you need a device which is of a certain category. And if the energies are high, you can apply a simpler technique. So the low energy technique is that you let the particle hit a surface which is capable of producing a lot of secondary electrons, and you count the secondary electrons. So you don't, detect the particle directly. You let it fall on a surface which generates secondary electrons, and you count the secondary, or you collect the secondary electrons. So typically, one such particle hitting a sensitive surface will result in the formation of, say, 10 to the 5 or 10 to the 4 particles. And you can have a cascade of this process, 10 to the 4 going to 10 to the 8 to the 10, and so on, until you have a large number of electrons which can be detected by routine electronics. Okay, so that is roughly the idea. Okay, so the secondary electrons that are generated from sensitive surfaces, their number doesn't really depend on the energy. It just, there's a flux the moment the energy is higher than a certain threshold. So if you want to also determine the energy of the particle, not just say that there has been a particle or not just detect a particle, but also be able to say what energy the particle had, then you need a supplementary technique. And I'll talk about this supplementary technique a little later. For higher energy particles, you can use something as simple as a silicon diode, okay, a silicon PN diode, and let this particle get embedded in this diode or pass through the diode, depending on how thin the diode is. On the path or on its path, this incident particle will deposit some energy, it will lose some energy. And this energy will be converted into electron-hole pairs. And these electron-hole pairs that are generated in the crystal or in the silicon chip or the wafer or the diode can be amplified by some very sensitive electronics. And the electron-hole signal, the number of electron-hole pairs that are formed or the total charge that is collected, is actually a very good proxy of how much energy was deposited. So you can directly do an energy spectroscopy by capturing this particle or letting this particle pass through the wafer and measure the total charge that is generated. Okay, so for heavy energy particles, very simple semiconductor detectors work. But for low energy, you need some supplementary technique to get the energy or the mass. And the energy that we are talking about for this device, for this spectrometer, is in this range. It is actually lower than this energy. Okay, so we need to apply the first technique. Now, in order to understand what kind of technique is suitable, we need to go back to some electromagnetic. So in electromagnetism, you know that there is this very famous Lorentz force equation, which just says that the acceleration of a particle is a function of the cross product, or is a sum of the cross product of its velocity and the magnetic field, and is proportional also to the electric field, directly proportional. So d2r by dt squared is q by m, which is the species identifier, or it is characteristic of the particle. And there's a force term, which is a magnetic force, which is v cross b, and an electric force that does not depend on the velocity. Now, if you have particles, several particles with different m by q ratios, then these trajectories or these r of t kind of equations are going to look different. But particles of the same m by q ratio, but with different kinetic energies. So remember, the same m by q ratio, but different kinetic energies, will have different trajectories and will also require different times to travel a fixed distance. So these are usually called spatial dispersion and temporal dispersion techniques in order to separate particles of different kinetic energies. So you launch a particle with a given kinetic energy, given mass by charge ratio. If they have different kinetic energies, their trajectories will be different, or the time taken will be different, or both will be different. And you use this fact to separate the particles according to the energy. So it's like a filter, really. What one should remember is that electrostatic fields, so fields which are purely electrostatic, will disperse particles according to their energy to charge ratio. On the other hand, magnetostatic fields disperse particles according to their momentum to charge ratio. Now, if you are clever, you can use a combination of electric and magnetic fields to achieve energy separation, momentum separation, and mass separation. I'll not again go into the details, but I'll just show something by example. So you are all aware of parabolic motion in the Earth's gravitational field. So imagine a particle, a projectile that is launched at an angle to a field. Now here I am showing an electric field, but in the case of projectile motion on the Earth, this is the Earth's gravitational field. Here I have generated the electric field by a parallel plate analyzer. The upper plate held at one potential, the lower plate held at another potential. I launch a particle at some angle, let's say 45 degrees. Then if the particle has a certain energy which matches in some form the field that I applied here, then it will have a parabolic path and the particle will emerge at a fixed point on the lower plate. So if I have a small hole here and launch the particle here, and I place another hole at the other end, then for some particular energy, this particle will emerge through the other one. So from a source, I'll get an image. A particle traverses this path and emerges without getting lost. If the energy is too high, then the particle will go further and will hit the plate and will be lost, will be destroyed. If the energy is too small, it will form another path which is shorter and it will again not emerge through the hole. So only particles of a fixed energy will emerge from a hole whose distance is known to you. So if I have a source here and I place a detector here, by changing the electric field, I can let particles of different energies be transmitted through this analyzer. So that's a very simple trick that people use. Sorry. The other trick that can be done is you take this parallel plate and bend it into a circle, a semicircle. Not even a semicircle actually, an arc. So what you will now have is that the same electric field is now a radial electric field. It is no longer a flat field and it's no longer a parallel field. It's a radial field. But now the beauty is that because this is a radial field, instead of doing this hole-to-hole transmission, you can have a radial passage in which only a particular energy is transmitted without loss. Higher energies are lost by hitting the walls. The other beauty is that even if the incident particles are not exactly radial, not exactly tangential, they have a slight angle to the tangent. Even then, because of this effect of the electric field, they'll all emerge as a point image at the other end. The only condition is that you have to satisfy that the included angle of this sector has to be pi by root 2, square root of pi by 2 radian. So these are some tricks that people employ. And the basic idea is that you apply an electric field which will ensure that the path of a particle is the one you want only for a specific energy. If you change the electric field, a new energy particle will pass through without getting lost. And that way you can scan the energy range by changing the electric field. Okay, so this is a very common technique that is used in mass spectrometry and things like that. Now let me just change the geometry of this system, and instead of a parallel plate or a parallel plate bent into an arc, what I do is I take two hemispheres, okay, an inner hemisphere and an outer hemisphere. They are not connected. Okay, by the way, these lines might suggest that they are connected, but they are not connected. There is an inner hemisphere and there is an outer hemisphere. I apply a field in the gap. So outer hemisphere is held at a constant potential. The inner hemisphere is held at some other constant potential. Usually the outer hemisphere is grounded and the inner hemisphere has a potential. Then near the north pole of this hemisphere, I make a hole and I put a small cap on the top. Now there's an electric field between this top hat plate. It is called the top hat plate because it looks like a hat. there's a weak field here because this is at a certain potential and this is grounded. So if an ion enters this gap, it will get deflected. Once it enters the gap, there is a stronger electric field in this gap between the outer hemisphere and the inner hemisphere, which causes a constant deflection of the particle inwards. If the electric field and the energy matching is achieved, then particles of a certain energy will pass through as if there is no force on them. The forces are balanced. So they will take a arc. The path will be an arc, and they will emerge at the equator. So this is again an energy filtering, very similar to what I described earlier. But the advantage of this configuration over the previous configuration is that this line, this dash dot line that I've shown over here, is an axis of azimuthal symmetry. So this instrument is able to accept particles from all directions. In the previous case, you could only send particles along one direction. Particles going along different directions could not be admitted. Here, there was a slight improvement over that. But in this case, all particles that are entering this gap in this horizontal plane, okay, in this horizontal plane, all of them will get accepted. The ones that come from this direction will emerge through the hemispherical gap here. Something that is coming into the plane will take a curved path coming out of the plane, but again emerge in the equatorial plane. So there's a complete azimuthal symmetry in this configuration, and that improves the efficiency of the collection very drastically. And more importantly, it gives us a way to measure the angular distributions, which is what we are interested in. So our instrument looks something like this. Okay, so there is this top hat electrostatic analyzer, which is the upper part, which is what I described. That is the first part of the instrument. What we also want, if you remember, is we want to be able to separate different charged particles like protons and alpha particles. Remember again that if you simply have an electric field, the electric field is sensitive to changes in the E by Q ratio, the energy by charge ratio. It is not sensitive to mass. So all particles, irrespective of their mass, will pass through this hemispherical gap undeflected if they have the same energy. So a proton whose mass is 1 unit and a helium whose mass is 4 units, they will both pass through undeflected if their energy is the same. Okay. So how do we achieve separation? I had mentioned earlier that if you use a combination of electric and magnetic fields, you can do this. So now, what we should note is that particles that have emerged through this upper hemisphere, this top hat analyzer, when they emerge here, all of them have the same energy. The ones that have a different energy hit this wall somewhere and they are lost. So everything that emerges here has the same energy. If they have the same energy, their momenta are related to their mass. Right? P squared by 2m is E. E is constant. So if their m is different, their P also must be different. So now you put a magnetic field which is sensitive to the momentum by charge ratio. So for a given energy, protons will get deflected more in the magnetic field and alpha particles will get deflected less. What should be the direction of the magnetic field? The magnetic field direction has to be into the plane of the paper or out of the plane of the paper. Remember, this is a this is an azimuthally symmetric configuration. So you spin this entire diagram about the vertical axis and you will get a cylindrical geometry. And these magnets, which are shown as trapezoids here, they are really several trapezoids placed along the azimuth. So you get a circumferential magnetic field, a magnetic field that emerges tangential to this point, perpendicular to this plane of paper, which I have shown separately in this diagram. Okay. So if I look at the bottom of this, look at this device from the bottom, I placed multiple magnets. There are 16 magnets, which create a circumferential magnetic field. Okay, so this gray band is the line of the magnetic field. Okay, so the magnetic field lines are circumferential. A particle entering the gap gets deflected inward, radially inward. The proton emerges at a greater distance from the circumference, and an alpha particle emerges at a shorter distance from the surface. So particle deflection is inversely proportional to the mass. Well, root mass. So here you get alpha particles, here you get protons. So putting a magnetic field sector which is composed of 16 16 permanent magnets arranged in this fashion will give us a device that not only filters particles according to their energy, but also separates them based on their mass. What now remains, the third challenge in our instrument, is the angular distribution. Now, a particle coming from this direction and a particle coming from this direction are coming from different directions as far as the instrument is concerned, and the instrument must be able to distinguish between the two. If a particle emerges at some other azimuthal angle, we should still be able to do something about it. So what we need is, at the bottom of this instrument, we have to be able to locate where the particle was finally detected. So it's really like taking a photograph. You want a photograph in which protons appear protons of a certain energy will appear on a ring. Alpha particles of the same energy will appear on a larger ring. If there's a heavier particle, they'll all appear on an even bigger ring. But if there are more alpha particles here and fewer alpha particles here for the same energy, I'll be able to say that there is an anisotropy in the distribution, and that is what I want to know. So my detector over here, which is counting these particles, now the detector's job is not to measure the energy. The energy is filtered over here. The mass is separated over here. This detector's job is only to count. But the detector's job has to now be enhanced, and not just limited to counting. It has to count and also give me the position of the particle head. And that is achieved by what is called, a microchannel plate detector, and that is what we employ in our instrument. We have two such instruments because, if you remember, we are only talking of one azimuthal plane over here, and in order to get a complete coverage of the solar flux, we need two of these. One which is aligned to the plane of the orbit, which is called the ecliptic plane. Well, aligned meaning parallel. And the other one which is across the plane of the ecliptic. Two detectors which are sort of perpendicular to, or which have fields of view which are perpendicular to each other. So there are two top hat analyzers that we have decided to build, or we have already built it. There's a small difference between the two. The outer the electrostatic configuration is the same, and we have a mass analyzer only in one of them. We don't have a mass analyzer in the other, and this is primarily because of weight limitations and electronics limitations. It would have been nice to have two absolutely identical detectors, but we have compromised here by not having a mass separation, so that will affect some of our observations.
Excuse me, sir.
Yeah.
I'm very sorry to interrupt, but can we take up more 5 minutes, because we
I'm
done.
I'm almost done. I'm almost done.
Yeah.
Okay.
Okay.
So these are two instruments that have been built, and these are now being tested, and not just tested. Okay, I'll skip this. They are not just being tested, they have been tested already. We are carrying out different tests related to thermal behavior, related to electromagnetic interference, related to how they perform after being exposed to radiation, and so on and so forth. These are the two packages, very compact packages, about 110 millimeter diameter. They'll be mounted on a bracket, which will then go and sit on the satellite. And these instruments will constantly look at the sun, one in the vertical plane and one vertical meaning the plane perpendicular to the ecliptic, and the other one parallel to the ecliptic. This is a cutout of the instrument. This is the magnetic sector. This lower one is the detector, where you can see different sectors. These are 16 sectors corresponding to the 16 magnets. The top part is the top hat analyzer that I talked about. The second one, which is the simpler one, does not have the magnetic part, the magnetic analyzer part. It will only do the energy analysis. So all of this has been put together, and what we expect to achieve is energy spectrum in this energy range and a full coverage of all angles, and also cover all masses, but be able to separate protons and alpha. We are not interested in separating out the heavier particles. That would not be possible in this small extent. Here is a test spectrum. You can see that the different masses are quite well resolved, especially proton, which is here, H2 plus the molecular hydrogen ion, and the helium ion. These are well resolved. The heavier masses like neon, argon, and so on, which are part of the test phase, these are not well separated. Their separation is not great enough to be able to say very clearly. But we are not interested in that. We are mostly interested in the ratio of this to this or this to this. Okay, that we are able to achieve. We are very happy about that. We also have different tests which will make sure that our calibrations are correct. And another important thing, which is that we need to know whether our energy filtering is happening properly. And you can see that different energy particles will pass very cleanly through this. You get different bands of different energies. So if you have a complete spectrum all the way from 0 to whatever keV, we'll see a nice distribution. These are for discrete energies, but if there are continuously varying energies, we'll see a distribution. That is something we have tested and are quite happy about. Lots of data will come in different forms, and the data volume is quite large, but we are very happy that we will be able to support such a large data transfer from the satellite. And ultimately, what we really hope is that once this satellite is launched, which will be sometime in mid-2022, after a 6-month journey, the satellite which is going to look like this finally, will start giving us data in two planes which are indicated here. Give us proton alpha separations, proton alpha ratios, angular distributions, and energy spectra of solar wind. I hope that sometime from now I'll be able to come back and tell you about whether this entire project has succeeded or not. Thank you.
Thank you, sir. It was a very wonderful session we had, and like we can take 1 or 2 questions right now due to the time constraints.
Yeah.
So if anyone has a question, they can raise their hand or put it in the chat box.
Let me look at the chat box.
I don't think there is anything in the chat box. So if I can ask a question, like the project that Isaac is working on is detection of alpha particles and protons, but like can we have like the instrument is just solely sensitive to alpha particles, or we can do some other things as well, or from the data make out some other inferences as well?
No, so see, as I said, I mean, depending on how you configure the instrument, if you want to say detect some heavier particles, like say some other nuclear, not proton or helium, but say lithium or iron or silicon that is coming out of the sun's in the solar wind. These are of course very small fractions. Then you will need a corresponding analyzer which will be able to separate those species. Our analyzer currently is not capable of separating them. You will need to employ different techniques. Okay, so different species, different energy ranges require different techniques for detection and separation. Okay. So then it is not possible to have one single technique which will cover all possibilities.
Okay, sir. Yeah. So I guess if we don't have any more questions coming in, I guess there's one.
Okay.
Okay, so like we can commence this lecture, and we'll love you if you can, after this pandemic gets over, you can come visit the college and interact with us.
Sure.
And now, okay, would like some Astro Club with the co-host to add some few words.
Okay. So thanks a lot, and I hope to make a trip to the college sometime. Okay. Bye.
Yes, sir. Thank you so much.